Now, another potential solution for this is to violate the filtering rules inbound on router 5 to use the allow AS in, and we can say how many particular instances of our own autonomous system do we want to allow. But again, the problem with this is that this would only work if the remote PE router was regular iOS as opposed to iOS XR. And the reason why is that XR is applying this as an outbound filter where it said router 4 was in AS 456, don't advertise them routes that contain 456. Where from router 1's point of view, it says just advertise them anything, and then, or advertise them everything, and whatever they don't want, it's up to them to drop it as an inbound update. So from router 5's point of view, we could go under the BGP process here, BGP 456, and we'll say that for the neighbor 10.151, so this is router 1's address, we want to allow our own AS in, and again, we could say how many particular instances or how many occurrences will we allow. So by default, I believe that we're allowing just one. Allow AS in. It doesn't say there, but I think it's just one instance. And if we now look at the show IP BGP, we should see that even though our own autonomous system is in the path, we're now allowing those particular prefixes in. So from router 5's point of view, we should have reachability to router 7. And actually, we would have the same problem on router 7 because 7 is now in 456. So from 7's point of view, if we look at the show IP BGP, we're not receiving router 4 or 5's loopback because it's filtering those inbound again because of the autonomous system path. So let's now say from router 3's point of view, under BGP 1, when we're peering with 7, we're going to do the AS override. And this is going to be under, not under global BGP, this is going to be under address family IPv4 VRF-A. Neighbor is 10.377 and AS override. Okay, then from 7's point of view, if we clear IPBGP star inbound and show IPBGP, we should see that we're now receiving those updates, and we now should have reachability from 5 to 7, from 5 to 4, and then likewise from 4 to 7. So again, notice from router 7's point of view, the end result is that it doesn't see its own autonomous system in the path because it's been overridden by the service provider's autonomous system number. Now, in certain cases, though, you may not want to do this, really depending on what the peering design is between the provider and the customer. And an example of this would be if we have the same BGP site that is multi-home to the same provider, and we are doing AS override at the same time, there is a potential for causing a loop or, at a minimum, a suboptimal routing in the network. So in our particular case here, between routers 4, 5, and 6, we have AS 456, and then between 3 and 7, we have likewise 456. But we're doing the AS override, so we're replacing this with 1. But the problem we could run into potentially now is that as router 5 learns a route from its internal BGP peers, let's say router 6 in this case will run iBGP between 5 and 6. When router 5 advertises this out to the rest of the PE routers, there's now nothing stopping this update from going to 1, and then from 1 to XR1, and then from XR1 to send it back to router 4, and then have the update be advertised in this direction. Now we'll see, it really depends on the BGP path selection, which route is going to be chosen as the best path, because those are the only ones that we can advertise. But there are situations where you can set up the BGP policy that this will cause a problem, and since we're breaking the AS path loop prevention, we then need to introduce some additional sort of loop prevention. So first, let's go ahead and look at the problem, and then we'll talk about what are the specific resolutions for this. So next, what we're going to do is between routers 4, 5, and 6, we're going to enable IGP on their links between them. So let's say we're going to run OSPF on these 3 interfaces, and then we're going to do BGP peerings, let's say that router 6 is going to be our route reflector for IP version 4, and then we're going to advertise the loopback of router 6 into the BGP process. So we're going to be running iBGP as well as IGP on these particular interfaces. So from router 6's point of view, let's look at the show IP interface brief. And we should have reachability to 10.4.6.4 and 10.5.6.5, which is router 5 and router 6 respectively. Okay, so first we're going to go to these interfaces, which are gig 1, 46, and 56. And we're going to run IGP, so let's enable OSPF. And the reason that we need to enable OSPF is going to be for our BGP next hop recursion. That when router 4 and router 5 have routes reflected to each other, the route reflector is not going to be updating the next hop value of the BGP updates. So either we would need to configure the reflector to manually change those next hops, or we would need to give the iBGP routers a route to the next hop. So simple solution here is that we want to run IGP in conjunction with iBGP. Okay, so in this case, router 5 was pre-configured with OSPF there. And then we'll go to router 4, and we'll say on interface gig 1, 46, we have IP OSPF 1 area 0. And then gig 1, 56 as well. Or no, not 56. Gig 1, 45. IP OSPF 1 area 0. Okay, so if we now look at the show IP OSPF neighbors, we should have adjacencies to 5 and 6 from router 4. From router 5, we have 4 and 6, and then from 6, we should have 4 and 5. Okay, so next we're going to configure our BGP peerings. So router 6 is going to be running BGP 456. We're going to peer with 10.4.6.4, so that's router 4 is an AS 456. And they're going to be a route reflector client. Okay, we'll also peer with 10.4.5.5. No, 10, this would be 5.6.5. Remote AS 456. They are a route reflector client. Okay, router 5 had already had this BGP peering configured, so if we look at the show run section BGP, we just have this additional iBGP peering configured over to router 6. And from router 4, then we're also going to peer with 6. So router BGP 1, or excuse me, 456. Neighbor is 10.4.6.6, remote AS 456. Okay, now additionally from router 5's point of view, when we look at the BGP config, we have a route map configured in from the provider edge router that's modifying our BGP policy. Where specifically in this case, if we look at the show route map, it says that we're going to set the local preference to 200, or in other words, we're going to say that when we leave the autonomous system, we're going to prefer to use router 1 as the exit. So when router 4 is routing to 7, we should see that the traffic is going to go this direction, because when we receive multiple updates in, we're going to have a local preference of 100 by default coming in from XR1, and router 5 is changing the local preference to 200, so router 1 is going to be our preferred exit. Okay, the end result of this is if we look from router 6's point of view and look at the show IP BGP, we should see that we're learning the routes to the other sites, which in this case specifically is 7777. Okay, next on router 6, we're going to advertise our own loopback into BGP. So we'll say network 6666. And then ultimately we want to get connectivity to 7777 and source the traffic from our own loopback. Okay, if we were to do a trace to this, we should see that the traffic is going to exit via router 1, because that was the one we have the BGP policy configured to prefer it as an exit point. Then we're going over the MPLS core. We're using a 2-label stack where the bottom label, number 32, is talking about the final destination, 7777. The top label, number 17, is talking about the egress PE, which in this case is router 3. So up to this point, it looks like everything's working fine. We have connectivity between the different sites, and we can see there's no type of loop in the data plane. Okay, next let's look at specifically from routers 4 and 5's point of view, how are they routing traffic within their site? So from router 5, if we look at the show IP BGP, it says I have a route to router 4, I have a route to router 6, and these are reachable through my, router 6 is reachable through my internal peer, which is 10.5.6.6, where router 4 is reachable through my external peer, which is router 1. Okay, also on router 5, if we look at the show run section BGP, in this case we're doing allow AS in, and I'm going to change this so that between router 1 and router 5 we're doing AS override. Okay, so let's say on router 5 we're not doing allow AS in, and on router 1 we'll say under router BGP, under address family IPv4 VRF-A, the neighbor is 10.155, and we're going to do AS override. Okay, on router 5, if we then say clear IPBGP star in, let's look at the end result of this. If we show IPBGP, okay, now when we're receiving those routes inbound, we're receiving them from with a path that is 1.1 as opposed to 1.456. So from router 4 and router 5, when we do a trace between their loopbacks, and we source this from our own loopback 0, notice in this case the two edge routers of the customer edges are going to the MPLS network in order to route within their own site. Now, likewise, if we look at this from router 6's point of view, and we were to trace from 6 to 4, the traffic is going from 6 to 5 to 1 to XR1 and then to router 4. Or in other words, traffic within the site is going through the MPLS WAN connection in order to locally route. So we would figure that from 6 to 4 we would go directly that direction, but instead we're going this way. Now again, the reason why this is happening though is based on the BGP policy, that router 5 was trying to be used as a preferred exit point, and the way that we were doing that was to change the local preference to be a higher value. So this means that from router 6's point of view, even though it's learning both routes for 4444/32, we have the one that's coming from router 4 directly, it has a local preference of 100. We have the other route that's coming from router 5 with a local preference of 200. So the end result is that we choose that as the best route, even though that's not going to be the shortest internal path between the neighbors. Now, really, whether this is a problem or not depends on the scope of the question within the exam, because if the goal is just to get reachability between the neighbors, we've established that. There's no problems with that. But if there's also an issue with specific routing directions, like if we want to say between router 6 and 4, we want to use the direct link between them, and we don't want to go out to the MPLS VPN and back, this is what the BGP site of origin feature is designed to fix. So the idea here is that we have the same customer AS, where we have AS 456 on this site, and we also have 456 over here. And the problem we ran into is that when router 7 advertises its loopback, goes from 7 to 3, 3 to 1, 3 to XR1, and then when we go to advertise this outbound, the update is dropped because it has its own autonomous system in the path. So the fix for this is we said from router 1 out to router 5, from XR1 out to router 4, we're going to do the AS override. So we're going to take AS 456 and we're going to replace it with AS1. So we saw that we had 7777 via AS1 and 1. But as a side effect of this now, when we're receiving routes from the internal peers, a route is going from 6 to 5, from 5 to 1, from 1 to XR4, from XR4 back this direction. And this update is going to be allowed in because it doesn't contain our own autonomous system in the path. So essentially what we now want to do is to selectively filter routes depending on which site that they came from. So we do want to allow the routes from router 7 site to go to router 4 and router 5, but we don't want the routes within their own site to go from 5 to 4 and from 4 back to 5. Now, the way that this is implemented is with an extended community. We don't necessarily have to use the site of origin to do this. We could apply this with a prefixless filter or with an access list, distribute list. We could do it with our own community that we are specifically tagging. But we'll see that the site of origin is a very simple solution for this because it's an automatic inbound and outbound filter for routes that contain this specific extended community. So the way to specifically implement this is that we'll say when we're peering from router 1 over to router 4, or from router 1 to router 5, we're going to say that router 5 is in the site of origin 456:1. So the format of the tag is an extended community, just like the route target value would be. So this means that when we receive updates in from the neighbor, we're going to set the extended community to 456:1. This update then goes out to XR1. XR1 is going to say likewise that router 4 is in the site of origin 456:1. So this means that if I receive an update in that contains this extended community, I'm not going to advertise that particular route back to router 4 because it is part of the same site. So in other words, if the route originated from the same site as router 4, we're not going to send that particular prefix back. And the configuration we'll see is very straightforward. From router 1's point of view, we're simply going to say that when we're peering with router 5, so if we show run section BGP, we'll say that under router BGP 1, for this particular neighbor, we're going to set the site of origin, SOO, to an extended community. In this case, we'll say 456:1. Now, before I actually do this, let's look at the show BGP VPN v4 unicast neighbor 10.155 advertised routes. Unicast all neighbors. And we can see that we are advertising the route 4444, which is essentially the looped path that we're advertising back to router 5. Okay, we're going to then apply the site of origin. So we'll say that neighbor is in site 456:1. And we're going to do the same thing on XR1. So let's look at the show BGP VRFA IPv4 unicast neighbor 10.4.11.4 advertised routes. And in this case, we're not advertising router 5's loopback, but this really depends on what the path selection is of the PE router. So from XR1's point of view, if we show BGP VRFA IPv4 unicast, and we see that we're receiving 5555 both from router 1 and from router 4. Since we're choosing router 4 as the best path, it means that we're not going to be advertising that particular prefix back to the eBGP peer. So really it depends on, does the provider itself have a different BGP policy that we're preferring one route or one link to the customer over another one? And then if we're changing the best path selection, that's going to affect how we're updating or how we're sending those particular updates out. Where it just happens to be in this particular case that router 1 is advertising 4444 out to router 5, because if we show BGP VPN v4 unicast for VRFA, we see that we are only learning 4444 in from 11. We're not learning it directly from the customer. And again, the reason why that is the case is that from router 5's point of view, we're saying when the update came in this way, set the local preference to be 200. This means that when 5 advertises this to 6, 6 says, I'm going to prefer this as the best route, which means the advertisement that is going from 4 to 6 does not get chosen as best and does not get advertised. So the end result is that router 1 does not know that 4 is reachable this way. Instead, router 1 only says that 4 is reachable that way. Okay, so next on XR1, let's go ahead and apply the SOO as well. So if we show run router BGP, we're going to say that under BGP 1, under this particular VRF for this neighbor, under address family IPv4 unicast, we're going to say the site of origin is 456:1. Okay, next if we go back to router 1 and we look at the show BGP VPN v4 unicast all neighbors 10.1.5.5 advertised routes, we can see now we are no longer advertising 4444. The reason why is that it contains the same site of origin tag, or the extended community more specifically, that router 5 is configured with. So when we look at the show run section BGP, this neighbor is tagged with SOO 456:1. And if we now show BGP VPN v4 unicast all 4444/32, this also contains that site of origin, which means ultimately we're not going to be advertising it to that peer. Now, likewise, this means that if router 1 does not advertise it to 5, 5 cannot advertise it to 6, 6 does not choose it as the best path, and then it means that we will now learn from router 5's point of view, we will learn the path that is reachable through router 4. So from router 5, if we were to now look at the show IPBGP, we see now the next hop for router 4's loopback is 4. And if we trace to 4444, source from our own loopback, we see we route within the site as opposed to routing between the sites. Now, as someone had also mentioned here, there is a problem, though, that in certain failure situations, the site will be isolated from using the MPLS network as transit. So what I mean by this is that if we were to lose the link between router 5 and router 6, we would not be able to route from 5 to 1 in order to reach router 4. Because ultimately, when the update is going this direction, we're tagging it with 456:1, and those are not going to be allowed to go back from router 5 to 1. So we could see this if we were to go to router 5, and let's do a ping for 4444, source from the loopback, and we'll do a high repeat count. If we now go over to router 6 and we disable the interface that goes to router 5, which is gig 1.56, this should mean that we lose the BGP update, and we can see now the traffic is going to be black holed. Because from router 5's point of view, if we now show IPBGP, or more specifically show IP route for 4444, it says that we are learning this from 10.4.6.4. And if we go to router 4 and look at the way back, show IP route for 5555, the path has been withdrawn. So eventually router 5 is going to figure this out once the BGP timers expire, and then the BGP session is torn down from router 5's point of view, but we now only have basically one-way transport because we cannot use the MPLS network as transit between them. So again, within the scope of the lab exam, it really depends on what the questions are asking for. If the question says that we do not want to use the MPLS network as transit, then this is one of the potential solutions. Is simply to say that when I receive routes from the site, I don't want to advertise them back to the site by using that extended community, the site of origin, to say it's an automatic filter outbound to the neighbor. Okay, there's a question here, which direction is the site of origin applied? It's applied in both ways. So it means that when you receive the route in, you're setting the community, and when you go to send updates outbound, you are matching the community and then doing a deny. So if you think about this in terms of regular IGP routing, it would be the equivalent of doing something like this. That if we were to say we have a route map that is going from BGP to the CE, says to, or to, let's say from the CE. BGP from CE says set community 456:1. Okay, now it's not this exact syntax, but you get the gist of it, that we're doing some sort of tagging. Okay, then we have a route map that is BGP to the CE. It says deny 10. Match community 456:1. And then to permit everything else. So we would then say under BGP, whatever the neighbor is, route map BGP from the CE is in, and the route map BGP to the CE is out. So again, you don't necessarily have to use site of origin. You could use some sort of manual policy like this. It's just that site of origin automatically applies this type of filtering logic, that we're setting the tag value or setting the community when the route comes in, and we're saying before we advertise them routes out, see does the prefix have that community, and if so, then it's going to get denied. There's a question, is site of origin only applicable to VPN v4 routes or also IPv4? I don't think that you can apply it under the IPv4 address family. Let me take a look though. So let's say under router BGP1, address family IPv4 unicast, and the neighbor 1234. It does have it, but the typical issue you would run into is that with regular IPv4 unicast peers, you typically don't exchange extended communities. So if we notice here under the VPN v4 neighbors, when we look at the show run section BGP, between router 1 and XR1, the default behavior is that we're sending communities and we're sending them as extended communities. So you could potentially do that between the neighbors in IPv4 unicast, but you would need to make sure to say send community extended or send community both on both sides to make sure that the tag value actually gets included in the update. But otherwise, you could write this as a manual policy. You could say route map X to set the extended community, and we'll say the site of origin is 456:1. The example that I'm doing is just we're applying it to all routes as opposed to specific routes. You can do this for a subset of prefixes. You could say maybe I only want to tag 6's loopback with the site of origin 456:1, and you would do that by calling the route map or calling the route policy and then matching that particular prefix. Okay, within the case of iOS XR, this would be under the routing policy language. So we would say something like we want a route policy that is to set SOO, and it says if the destination is in 6666/32, then set the extended community, and the extended community is the site of origin 456:1. Okay, then we'll say else to pass. So if we look at this output, this would be the same effective type config as using a route map with a match prefix list on iOS, but you can see the syntax is different here. So it says if the prefix is 6666/32, then set an extended community onto it, and specifically it's the site of origin, and the specific value is 456:1. If it's not this prefix, if it's anything else, then simply allow it, pass it through. Now also someone asked the question, how does this affect router 7? From router 7's point of view, since it's not being tagged with that site of origin, we still see that we have connectivity to both of the sites. So if we ping to 4444 or 5555, 6666, etc., we're still going to have transport, and this is going to go over the L3VPN.